Welcome back to Python for Machine Learning. Let's discuss deep neural networks now. As usual, this is a QR code which points you to the website and the GitHub repository that contains these slides and the material which you need otherwise. So what are deep neural networks? Basically, they're just multi-layer networks with many layers. You see a graph representing the evolution of the error rate of an image recognition software over time and annotated with the number of layers which were used in the neural network. And you see on the right that it evolves from an error rate of over 25% with shallow networks to, on the left, a network that has less than 4% error rate and 152 layers. So gradually, from right to left, the number of layers increases and the error rate decreases. This makes a huge difference, because a system with an error rate of less than 4% is quite usable in practice, while, for instance, if you have an error rate of 10%, you still have to do quite a lot of manual work, which typically means that the system is not usable in practice. So, another important aspect of deep neural network is that features are learned by the neural network rather than being given by the data scientist deploying those networks or training those networks. So, feature engineering, extracting features from the data using whatever means and feeding those into a neural network is not typically the way deep neural networks operate. They learn their own features, and we'll see an example of this shortly. The idea is that low-level features get combined into high-level features as the information goes from the bottom of the network, where the actual input is, to the top of the network, where we have the final classification, for instance, for classification task. There are also some special type of layers, for instance convolutional layers. This we will discuss in a minute. Dropout layers, which we already discussed in the last part of this sequence, and recurrent networks, which will be the subject of the next one. Let's have a look at convolutional networks. So basically convolutional networks try to detect very low-level features of images. Again, we use the MNIST dataset as an example. So this would be a handwritten 5, and we have a very small window which slides over the entire image, and which in this case is rather simple. It's a very small matrix, let's say a 5 by 5, a 3 by 3 even, which is the unity matrix. So it has 1 on the diagonal elements, 0 on all the other elements. So we just slide it over the image, doing the element-wise multiplication, and we get the following result. So basically the feature which is extracted by this kernel is in fact diagonal lines from top left to bottom right. Some other examples. So this is the one we already seen in the previous slide, and that would indeed select features that are diagonal lines from top left to bottom right. This would be another example. It's the matrix that has 0 everywhere except on the other diagonal, so that would be all ones. And then you see that what gets selected is in fact similar lines but slanted the other way around. This is yet another example, but now on a tree. So basically you see which features get selected by these matrices. Now these matrices are not given up front, they are in fact also learned by the neural network. So the deep neural network will in fact learn which features to extract using this kind of convolutional technique. So the second approach to our digit identification task is starting from a grayscale image again, but now we'll operate on the 2D array as it is given. The reasoning here is that the spatial relationship between the various points in the various pixels in the image is in fact preserved, and that the local features will in fact be combined into higher level features, improving the image recognition task. And the output data will be the same. That will just be a one-dimensional array, one-hot encoded. So that's not different. So the model we will build is a convolutional neural network. It will have 28 times 28 inputs, then a convolutional network layer with 32 filters 3 by 3. So each of those are 3 by 3 matrices, which will be learned, and we've got 32 of those, so we get 32 low-level features detected. We use a rectified linear unit activation function, then a flatten layer, which basically means that we turn 28 by 28 into a 784 layer. And then we have a dense layer finally with 10 units, and the softmax activation function, just like in the previous approach. Obviously, this network is not particularly deep, it's just to illustrate the use of a convolutional layer. And typically you would have quite a number of layers in order to do a more sophisticated classification task. So let's use a convolutional network to recognize handwritten digits. As usual, we have to first do some data preparation, and we need to load some modules in order to do that. There is nothing particularly special here, except the one thing which is interesting is in the data preparation. So depending on the backend, the number of channels rather, is either the first or the last dimension, and that depends on the backend. However, the backend can inform us of that, so that we can create the right shape in order to reshape our data. As usual, we load the training data and the test data. And we can start pre-processing our data. So as usual, we define a scikit-learn pipeline in order to do that. We reshape the input data according to the shape which we computed, and we also convert the unsigned integers to floating point numbers between 0 and 1, just like we did in the previous multi-layer approach, multi-neural network layer approach. But now we combine that into one transformer rather than into two. So we apply the transformer to the training data, where you do a fit, and we don't do a fit for the test data, as usual. The output has to be reshaped, it has to be one-hot encoded, and we also change the type to floating point, just like the previous for the multi-layer perceptron. So basically we do that for input and output. And again, we split our training data into training and validation, as we did before. We check the shapes, and we see that indeed we've got 45,000 inputs and output pairs for training, 15,000 input and output pairs for validation. And we have a 28 by 28 image with one color channel, of course, because we had grayscale. Let's verify whether things still look okay. So this is our first training example, and indeed if we just plot that, we get 6 in this case, and the output is also 6 in sparse representation. So now we start building our simple CNN. We need to load a number of modules as usual, and again we set the random seed for the TensorFlow backend so that we're sure that things are reproducible. Then we can build a model. As usual, it's a sequential model, and we start adding layers. So the first layer that we add is a convolutional two-dimensional layer. So hence conv2d. We specify the number of filters, that will be 32, and the dimension of the filter, the individual filters, as a tuple. So in this case we use 3 by 3 filters. And we have a padding which we set to valid, which means basically that we will kind of drop the outer, upper, lower, left and right row of our image. This we have to do because otherwise our kernels don't have enough data to operate on. The input shape is of course the shape which we computed from the backend. Then we add an activation layer, which is again rectified linear unit, and we add a flatten layer. So basically all those two-dimensional layers will be turned into one long one-dimensional layer. And then we have a dense layer with 10 units and an activation function finally, which is softmax to compute our probabilities for the different classes. We can have a look at the summary of the model. And as you can see, there are a number of parameters, but not that much. So basically the convolutional 2D layer has 320 units, parameters, so there are 32 of them, and each is 3 by 3, so that's 9 plus 1 for the bias. Okay, then we can compile the model. There is nothing special here. Again, we use categorical cross entropy, just like the last time. We again use an SGD, so stochastic gradient descent. However, we set the learning rate to 0.1 and the decay to a very low value. And we have some momentum, and we want Nesterov normalization. And as accuracy, we have again, as metric, we have again the accuracy. So we can then fit the model, and we only have 10 epochs here. So the batch size is 32. This is a good number for most cases. Setting the batch size is a bit of black magic, let's say. And as you can see, the model is being trained again on my 1-core 250 GHz CPU. So, after a while, the 10 epochs have been computed, and as you can see, the accuracy on the training data is again 99%. That on the validation data is 97 and a little bit. So this is quite good. Let's have a look at a plot of the metrics. We first define the function, and then we plot the actual metrics. And as you can see, the validation error more or less goes a bit all over the place. So that goes for the loss, and that also goes for the accuracy. This is somewhat worrying. Although the results are not bad, I'm slightly suspicious because we would prefer that the behavior of the validation loss and the training loss and the accuracy of both are more or less similar, and that does not really seem the case. So we might have overtrained our network a bit. So let's evaluate on the test data. And we see that we get 97%, so a bit lower than with the multi-layer perceptron. However, note that we did that actually with 10 times less training epochs. So that is quite interesting. And as usual, we may save the model if we want to for later experimentation and analysis. So let's improve the model a little bit by adding more layers and also adding dropout in order to avoid overfitting. So the first layer of the model is the same, it's a convolutional layer, 32 filters, 3 by 3, so nothing out of the ordinary here. Then we add the same rectified linear unit activation layer. We flatten, but then we add an additional dense layer of 128 units and an activation layer after that, which is again a rectified linear unit. And then we do a dropout with a fraction 0.1. Then we have our final layer, which is again a dense layer with 10 units, and the softmax in order to get our probabilities. So the summary. And as you can see, now of course we have quite some more parameters to fit. We compile the model, in this case just with standard SGD, no tweaking of the parameters, and we fit as usual. Which again will take a while in order to compute. Now of course it will be a little bit more expensive since we have extra layers in our model. Again, after a while, training is done, and as you can see, we actually get a much lower training accuracy, which is now near to 98%, but less than the previous. However, the validation accuracy is quite a bit higher, so indeed we avoided some overfitting using the dropout layers and also thanks to our more sophisticated model. So let's plot, and now we see a much more expected behavior of the training and validation error, and basically they follow the same pattern during the training epochs. So let's evaluate the model on the test set. And as you can see, we get a very good test score of 97.75%, which is quite good. So next we'll discuss a natural language processing task, sentiment classification.